Hello there. I intend to give 2 lectures on miniature fuses. The first will include the fuse types, the fuse thermal storage capacity, the I2t, and a few examples, the standards for fuses, the fuse breaking capacity, and temperature effect on fuses. That almost covers all the aspects of that small miniature fuses. By the way, the miniature fuses are those fuses you find in instruments and equipment, those small little ones, regardless to their body, if it's ceramic or glass. It comes in a 20 millimeter length and 5 millimeter in diameter, and the American types, it comes in 1/4 of an inch by 1 1/4 of an inch length. The second lecture will concentrate on using the I2t expression to protect semiconductors. So let's start by our first lecture. So what are the types of miniature fuses? We have that super quick acting FF fuses used for protecting diodes, SCRs, and triacs. Usually it's expensive and it's approximately 10 times faster than the F-type. That's for an I over IN greater or equal to 2, where I is the actual current going through the fuse. The IN is the normal or the rated current of that fuse. 2. Quick acting F fuses, called normal flow in American terminology, used as a low cost protection for semiconductors, used in circuits if little or no current surges are encountered, approximately 10 times faster than the T-type. See Fig 1. That's the figure we're going to talk about it later on. Okay, so the FF type is approximately 100 times faster than the T-type. i.e., if it takes 1 millisecond to blow an FF-type fuse, then it would take about 100 milliseconds to blow a T-type one for the same current. After that, we have that medium time lag M-type fuses. It's very rarely seen, by the way. Used where small transients or surges occur during normal operation. The time lag T fuses, called slow blow in American terminology, used where high inrush or starting loads occur, such as capacitive or motor circuits. Most power supplies, by the way, include this type. Also called anti-surge fuses. The F-type and the T-type are the most used types of fuses for protecting equipments. And the super time lag TT fuses provides even more time lag at high overcurrents than the T-type. This type is also very rarely used. Okay. Now, what are the things we should look 4 on a fuse. We should look for the type. For an example, if it's a T or an F, we should look at the rating, which is 1.6 amps in this case. We should look at the voltage of the fuse. It's 250 volts. And we have the approval symbol that belongs to the laboratory that approved that fuse. Okay. This information is usually engraved on the cover of that fuse, on the metal cover of the fuse. Usually you'll find this information engraved there. Okay. Now let's take a look at this figure, which is a very important one. It shows all the subspeeds. And types of fuses. Okay, let me just focus a little bit on it. This is a very good deal. Now this graph can be downloaded from many sites, or freeze the video and just take a good look at it. It is a logarithmic graph of time and current passing through a given fuse. The current in this case is a multiple of the rated current of the fuse, which is the I over IN. Note that a fuse doesn't blow when the rated current passing through it exceeds its rated current by even as much as 30%. That's for the T-type. That's for an F-type fuse. Or even it gets worse. It's even 60% for the rest. And this you can see up here. That's the F-type, 1.3 times its rated current, and that's for the rest. It's about 1.6 times its rated current. And this is coordinates with up to 27 hours. And you can see that line is vertical, so God knows how long it will take to affect that fuse. Now this fact contradicts what many think the fuse should do. So the fuse doesn't protect a device or an equipment from a moderate overloading. It only protects the device from short circuit or heavy overloading. So many transformers might be melting by the overloading, and that fuse knows nothing about it. That's a shocking piece of information, I believe. Okay. Now, just to see the relationship between the type of the fuses and the time they take to blow. This is the FF type, and this is the F type in here, okay? And you have the T type over there. As you see in here, it's a multiple of tens. So if this one takes, let's say, about 1 millisecond to blow, that would take 10 milliseconds to blow, and that would take 100 milliseconds to blow. So that means this FF type is 100 times faster than the T type. And this graph, by the way, is only for the glass-bodied types. Later on, we'll see the relationship between this type and the ceramic-bodied type. The glass-bodied type is a low rupture capacity type. Okay, let's move on. The fuse thermal storage capacity, referred to it by the expression I2t, its value specified in the manufacturer's literature. It stands for the value of energy required to blow a fuse, also called the fusing current, and the let-through energy. Its unit is in the amp squared second. The I2t of most miniature fuses can be considered fixed when the fuse is used in the range of 3 times to 10 times its rated current. That was displayed in figure 1, the previous graph that was presented. i.e., for a 1 amp fuse, the I2t is fixed for the range of 3 amps to 10 amps. The I2t of the fuse should be less than the I2t of a device being protected. That's in case the fuse is used to protect a semiconductor device or what have you. Okay, let's see now a few examples of the time relationship and the I2t of a given fuse. Okay, we have example 1. Now, to show that the I2t of a fuse is almost constant, regardless of the value of the current that is passing through it, as long as the I over In is greater than 3. That means as long as the current that passing through it is actually 3 times or more than its nominal current or its rated current. Okay, for an example in here, example 1, that's for a 1 amp F-type fuse, and the T equals 100 milliseconds. For I equals 3 times its rated current, 3 amps. So we have a 1 amp fuse. We are passing through it a 3 amps current. Okay, it should blow after 100 milliseconds. Now the I2t would be equal to 3 squared multiplied by 0.1 second, and that equals 0.9 amps squared second. The manufacturer's curve for that F-type that was displayed in first graph, figure 1, the manufacturer's curve for F-type fuse shows that for an I prime equals 9 amps, okay, so that's 9 times the rated current, T prime equals 10 milliseconds. Then the I2t would be 9 squared multiplied by 0.01 second, and that equals to 0.81 amp squared second, which is close enough to the above calculated value. So that proves that even though you increase the current through a fuse, still the I2t it's still considered to be a fixed value. Now let's see example 2. For a 2 amp rated F-type fuse and a T equal 100 milliseconds, and the I equals 3 times In, determine the value of T prime for an I prime that equals 9 times In. The same thing, it's a basic arithmetic, since we know that the I squared T is a fixed value, and we finally will come with a conclusion that T prime would equals 11 milliseconds. Now we go back to the figure, which is very close to the 10 that was presented in the figure. Okay. Now, in order for a fuse to blow, it must go through 2 stages. The first one is the melting stage, takes from 0 to T1, and the second one is the arcing, which is from T1 to T2. And the whole time, from T equals 0 to T equals 2, that's the time required for the fuse to clear the fault. So the time to blow the fuse is the addition of these 2 times. Let me just adjust the focus a little bit so the whole page can be seen. Okay, how to choose a fuse for a device. The I squared T value of the fuse should be about 50% or less for the I squared T of the device. I advise that the I squared T of the fuse should be about 50% of the I squared T of the device being protected. The fuse must carry continuously the device rated current. The fuse arcing voltage during arcing must be high enough to force the current down and dissipate the circuit's energy, i.e. the fuse rated voltage should be greater or equal to the source voltage. This means that the fuse must have the required number of notches or designed in a way to arc the required voltage to extract the energy from the circuit. That's all shown in figure 3. Where you have the arcs, it occurs here, and these are the little links. The T of the fuse, the T of the fuses in the expression I squared T includes both the melting and arcing times. Therefore, if the fuse voltage rating is less than required, the voltage buildup across the fuse or notches voltages summation is less, which makes the time longer to extract the circuit's energy, since the energy it equals to voltage multiplied by current and multiplied by time. So the idea that you have to have that enough notches there, so you will have stripes or notches to have that required voltage built across that fuse. So you have your rating the voltage in here in a way to lower the time and at the same time to lower the energy. Or the energy, by the way, it's fixed. It's the idea that the relationship between the voltage and the current and the time. Okay, now let's go to the standards for fuses. Or before that, let's see a basic schematic of a load where there is a need to protect a semiconductor device. And here you have the inductance of the wire. Actually should be the inductance of the whole circuit. Okay, and you have the resistance of the wire in here, and you have that fuse that's used for the protection. You have our load, which might be shorted or very overloaded, and you have that device which needs to be protected. And it's connected between the live and the neutral lines. Okay. So let's talk now about the standards for fuses. The IEC, International Electromechanical Commission, I believe most of the countries in the world, they follow the IEC standards. And you have the UL, the Underwriters Laboratories, that's the American Standard Lab. And you have the CSA, the Canadian Standard Association. Okay. Now, a bit of confusing information. It's that the American type of fuse does not replace the international type of fuse because they were tested differently on different standards. So if you have an American equipment, you have to make sure when you replace that fuse by international fuse, you have to know that they are not interchangeable. And here we see that the IEC fuse equals the Canadian or the American fuse divided by 1.25. So that means when you have a 5 amp fuse, 5 type, American type fuse, that you want to place it by an international one, you must put a 4 amp fuse. Okay, and that goes for both, for the T type and for the F type. And how do you know it's an American or an international fuse? First, if you know the equipment is an American, that's the first step. The second thing is actually just to look at that fuse. Like we said, these things will be engraved on the cover or written in the fuse somehow. It will tell you according to what standards that fuse was tested. Okay, let's move forward. Now to the fuse breaking capacity. HRC stands for high rupture capacity. LRC is a low rupture capacity. HRC usually for fuses, it's not usually, it's always, okay, for fuses that are ceramic bodied. LRC is always for fuses which are glass bodied, made of glass. Now, the F-type glass bodied LRC cannot replace the F-type ceramic bodied HRC. the operating time of HRC fuse is roughly equal to 1/3 of the operating time of the LRC fuse, which means the I2t of the ceramic type is 1/3 the I2t of the glass. And this is all shown in this figure in here. So that one in here is the ceramic, this one is the glass bodied, it's slow, and this one is the ceramic and it's faster. And the relationship is between 3 milliseconds and 10 milliseconds. Okay, so now even if you have a fuse that's F type, the body of that fuse also means something. That ceramic bodied is 3 times faster than the glass bodied. Okay, so they are not interchangeable. They are not interchangeable for two reasons. The speed, that's the first reason, and the second reason, we'll see it later. HRC can clear a short circuit current under the rated voltage without exploding. So it can be used in place where explosion might cause injury to people or damage equipment. The qualifying test for a 5 by 20 millimeter, 5 millimeter in diameter, by the 20 meter in length, fuse is to pass a 1500 amps at its rated voltage. So it must pass 1500 amps, okay, now regardless to its rated current, it must pass 1500 amps at its rated voltage without exploding. The LRC is used for low voltages or explosion does not matter. That means it might be housed, which is most of the case, must be housed inside the equipment or inside that plastic house of a fuse. So therefore it does not really matter if it's exploded there. The qualifying test for a 5 by 20 millimeter fuse is to pass 35 amps or 10 times its rated current, whichever is greater, at the 250 volts. Okay. So now the international fuse is not interchangeable with the American or the Canadian type of fuse. That's a confusing bit. Another confusing bit, that even if the fuse is an international and it has an F type, a glass bodied is not interchangeable with the ceramic bodied. That to fill in information. I hope you find them useful. Okay. Now let's go to the temperature effect on fuses. The temperature variation affects the fuses greatly. The fuses are made using metal elements, which means that their resistance have positive temperature coefficient, i.e. as temperature increases, the resistance of these metals also increase, and the P of the fuse also increases. So fuse value must be durated with increasing temperature, especially for the T-type. A T-type fuse rated 1 amp at 25 degrees centigrade becomes 0.8 amps at 70 degrees centigrade. There you can see this in here. Okay, that's 70 degrees. That's a 0.8 in here. So you have a 1 amp T-type at 25 degrees becomes 0.8 amps at 70 degrees centigrade. So if you intend to design equipment that operating in a very hot, let's say, climate or very cold climate, we have to know these facts. Now for the F-type, the effect can be neglected. It's almost a straight line. For the F-type, doesn't really matter much. The environment does not really matter much for the F-type. But the T-type, it's very sensitive. Similarly, The rated current of a fuse increases when operated at temperature lower than 25 degrees centigrade. And this is all shown in this figure. You can put more focus in that one. Okay. Okay. With this, I end my lecture. I hope the information that were presented were useful, and thank you for watching.